Good afternoon, everybody. This is a joint work again with my students and also National University of Singapore. Roger is a professor there, and Abdul Haq is a professor at Concordia, but he just recently started that position. He was a postdoc at National University of Singapore, and May is also close to finishing her PhD as well. So 2 days ago, we talked about the low latency live applications, how media over QUIC can help with several of those use cases, how we can actually establish and start streaming the video content as soon as possible, and not just at the beginning of the session, but also when we are sick, backward or forward, or when we need to do rate shifting, we can do relatively faster, so that the smoother video transitions we have, the better quality of experience we get. That was the whole goal, right? Media over QUIC might enable a lot of applications. Now, today's topic is not really based on QUIC versus TCP. We are indeed looking into real-time communication applications, which are, all kinds of video conferencing, really highly interactive applications like remote surgery, or if you are being treated by a remote doctor, that sort of thing, or online teaching, for example. I just taught one of my classes last night at 3 a.m. in the morning. It wasn't really very ideal, but over 2 continents, the latency still worked out okay. So coming back to my original, one of the slides I've been using for the last few years, now we are at the very edge of this figure. We are looking at the near real-time latency in the order of multiple hundreds of milliseconds. One of the things I would like to clarify, because a lot of us actually are confused about this, what is estimation versus prediction? What's the difference between those 2 things? So first of all, in any multimedia, real-time multimedia application, streaming or real-time communications, you do some measurements. You have to do some measurements. As you receive packets or as you send packets, you need to figure out what, how you are doing. And those measurements usually give you raw samples. And you can use these raw samples as they are, and some ABR schemes, they do that, Festi, for example. Or you do some sort of smoothing process, and then you use the past n values, and then come up with a smoothed value, and then you use those values at the end of the day. So the throughput-based rate adaptation algorithm in the -GS client is one of these. And these 2 approaches, using measurements, raw samples, or the smoothed values, are, as we call it, they are estimated values. But then if you take it one more step, and then if you do some learning-based, neural network-based process, and then you try to predict what is going to happen in the future, in the immediate future, that's what we call as prediction. And there are also relatively several schemes like that. So estimation versus prediction, there are some nuances, but maybe for the sake of this talk, you might consider them the same. So the challenge is we really would like to have an accurate bandwidth estimation in real time for real-time communication systems. So in a Zoom application, in a WebEx or Teams or Skype application, as we receive packets, we would like to figure out whether we should lower the bitrate or increase the bitrate that we are asking from the sender. Or if we are the sender, we need to figure out how much bandwidth we can use to encode our content. So we would like to improve our quality, obviously, right? And we would like to achieve still the low latency. We cannot really have too much latency budget for encoding. And we would like to minimize frame freezes. And then there are a lot of considerations which are detailed in our paper. And you need to look into video and audio quality at the same time. If there is desktop or presentation sharing, you need to look into that too. And then there is a frame generation time and then a frame delay. If the frames are not really arriving at constant intervals, you can still de-jitter them to some extent. But beyond a limit, you won't be able to do that. And the fact that you figure out how much bandwidth you have from that sender to that client doesn't mean that the encoder will be able to adjust to that bitrate right away. I mean, encoders, yes, they have rate controls and then everything, but they cannot just adapt right away. Maybe they are producing a specific frame type, and they really need a higher bandwidth, and then you say that you don't really have that much bandwidth, and the quality drops significantly. So there is some, there are some issues over there too. And then obviously the bandwidth fluctuations are very common. So this is a study from Alibaba, not our paper, but this was published last year in SIGCOMM. There are a lot of things that we can read from this, but comparing cellular networks with Wi-Fi networks and then wired networks, we realize that the last mile actually makes a huge difference when it comes to real-time communications. So the y-axis is 1 minus CDF. So if you take the opposite, it's going to be the cumulative distribution function. So between the Wi-Fi and Ethernet, so there's really not much difference between Wi-Fi and 4G. But let's look at Wi-Fi versus Ethernet. As you can see, there's a significant difference in terms of frame delays, and then also frame rates, like how fast you can, what's the number of frames that you can actually encode in real time, and the RTT. RTT can significantly increase in wireless networks, and then that might already put you out of your latency budget. So if your latency budget is 200 milliseconds, if the Wi-Fi delay is already 200 milliseconds, there's really not much you can do. So there have been a lot of studies. I'm not going to go into details. It's just, some of them are listed, and some of the authors are in this room. You can also talk to them. So this is not a new topic, but obviously we are really trying to push the envelope here. So the Bob bank on bandwidth algorithm that we have in this paper is a receiver-side approach. So receiver is the client that receives the data from a sender who is doing the real-time encoding. So on the receiver side, we receive the packets, we do decoding, and then we try to understand how much bandwidth we have. And then we figure out that, and then we let the sender know. And then the sender actually sees, checks whether it can actually, limit its bandwidth usage to that value. So the Bob controller is consisting of two subcontrollers. There's a heuristic controller based on the Google's congestion control algorithm, and then another one is based on the deep reinforcement learning, which is really an interesting controller. So as we receive data from the network, all these RTP packets, remember we are using WebRTC in this case, so it's all RTP packets. We input a number of things into our controller, and then we try to predict the bandwidth. What's going to happen in the next, several hundreds of milliseconds. And then, we compute that value. We give that information back to the sender using our TCP feedback. And then the sender is also running its own, loss-based congestion control algorithm. And then you have the feedback from the client. It looks at two values and then picks the minimum value, because you don't want to really overwhelm the network, as we have seen from the PCC talk yesterday. So the two controllers we have, heuristic and deep reinforcement learning, they have both advantages and disadvantages. So Google used to have only this heuristic algorithm, which is really simple to implement, but doesn't really perform very well in all the occasions. And DRL is not really that easy to implement. You need to do some training and all that. But then it is really able to adjust to Neve learning, Neve network conditions. So there are pros and cons to each other. And then the better training you do, obviously, the more performance you are going to get from the reinforcement learning controller. So how do we decide between, between these two controllers? We first, before we receive anything, we start with the heuristic one, because we really don't have any data about the network, so we just start with this. And then over time, we continue computing the value, the predicted value for both controllers. And then as long as the difference between two of them is relatively small, we keep using the DRL. If not, then we switch back to the heuristic one. It is that simple. Now, looking at some implementation and evaluation across different network profiles and then across actually a real internet testbed. We have these 5 network profiles, again from DeshIF, also from FCC. The famous Big Buck Bunny, obviously it's not an RTC content, but that's what we used. And then we are comparing this to the heuristic-based, the original Google's approach. Gemini, which was the winner of the Grand Challenge a few years ago in ACM Multimedia Systems Conference, and HRCC, which is another Grand Challenge submission. So on the right-hand side, you are seeing all these bandwidth profiles. So it's all kinds of mixed different profiles, and we are looking in terms of network scores, video scores. Video score is a VMAF score. Network score is a combination of packet loss, delay, and then a couple of other things. And we are trying to see how well we can actually, how close we can get to the actual value. So here, I'm showing only the LTE profile. The others are in the paper. So the actual bandwidth value is this red line, right? So it is varying significantly over the time. And then the other models are indicated with different colors here. And then if you look at the values, our approach is, obviously it's not doing a perfect job. You can't. I mean, there is no way to be able to track that bandwidth 100% accurately. The thing is, you don't want to overshoot, because if you overshoot, then you will tell the sender to use a higher bandwidth, and then that might actually result in some further congestion and some extra packet loss, which might cause some frame stalling. So you want to be as close as possible, but you also want to be really below the actual bandwidth that you can get from the network. Now, looking at the total score, which is again, combination of the video score and the network score, which is defined by Microsoft, who organized that Grand Challenge 2 years ago. You see 4 different approaches here. And the score is between 0 and 100. The higher, the better. And across different ranges, they are not really very similar, but they are not really too much different either. So, across different profiles, the performance gain is a bit different. Now, that's the test bed we use to train the model and look at the data and that sort of thing. But when it comes to the real implementation and testing, that's what Microsoft did behind the scenes. We just gave our code to them, and that's what they did. So this is the test setup they used in China and South Korea. So different links between their nodes on the Alpha RTC platform. You can also go to this website, opennetlab.org, and run your own stuff. So there are high latency links and low latency links, and then there are high bandwidth links and low bandwidth links. So overall, what really happened in this test was, again, these results were provided to us. Video score, network score, and then the total score. The bottom figure is a combination of the top 2. So video score higher. If it is higher, it means better video quality, right? And then, for example, in low bandwidth cases, we really couldn't do much better. But in the high bandwidth cases, we did relatively better than Gemini and HRCC. But the Google's congestion control algorithm worked just fine as well, right? In terms of the network score, which is packet loss, delay, and so on, there was a significant difference, because we are really trying to detect how much data we can receive from the sender, and then let the sender know about this, and then it adjusts the bandwidth, the bitrate it uses, and then hopefully there won't be as much jitter or packet loss. So overall, gains are relatively good, but in the high bandwidth case, as you expect, pretty much whatever you do, you are going to do probably fine. There are more interesting cases when there's not enough bandwidth in the network. So to sum up, this code is available. The paper is available. They are in the QR codes. Excuse me. So you can use this code yourself. You can look into it, open issues, such as improvements if you like. And if you have any other questions, you can reach any of us. Thank you.
That was a very nice talk, including the fact that you actually tested it with video quality. Any questions from the audience? If not, I'd have a question. It struck me that the heuristic, the Microsoft approach, was very conservative, and still it scores very well on the quality. Do you have an explanation for this?
Yes, there's an explanation in the paper, but the bottom line is that's, by the way, Google's heuristic approach, not Google, Microsoft. Sorry. Microsoft was the organizer for this Grand Challenge, and they deployed the testing environment Alpha RTC. And coming back to your question, Rob, yes, indeed. Because of the heuristic, the way it works, it tends to be conservative. That's the way it is built in. I mean, it is part of the congestion control algorithm. It's coming from the Google's congestion control algorithm, so it needs to be conservative anyway. You don't want to really overshoot and cause more problems in the network. So that's by design.
So it doesn't overestimate, and then
Yeah.
and that's
It
why
tries not to.
the quality
Exactly.
remains adequate. Okay.
Exactly.
Anybody else? There's still the chance to ask a question. If not, I
No?
would like to thank you
All
very
right,
much for
thank
this
you.
clear paper.